Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the voltage divider rule. Our objective today is to apply the voltage divider rule to simple series DC circuits to quickly and directly solve for unknown voltage quantities without having to solve for intermediate current and total resistance values. The key words are quickly and directly. This should appeal to those of you who have better things to do than to perform endless basic Ohm's law calculations to solve for required unknowns. Whatever you choose to do during this spare time is up to you, but the point is you'll have more time to do it if you learned how to use the voltage divider rule correctly. If the sheer amount of human drudgery the voltage divider rule promises to save you is not sufficient motivation to learn this technique, here's another factor that's sure to make the sale. It's my favorite technique. Now, when an instructor informs you that something is his or her favorite technique, you can be reasonably certain it will creep into every lecture, every illustrated example, every lab, every quiz, every exam, every workshop, every clam bake, and every kegger we have from this point forward, and it would behoove you to learn it. Keeping with the words quickly and directly, we're going to save ourselves some valuable time by referring to the voltage divider rule henceforth by its initials, VDR. Although this lecture deals exclusively with the VDR application to simple series DC circuits, we'll have ample time and occasion to revisit the VDR applied to various branches of series parallel DC circuits, series AC circuits, and branches of series parallel AC circuits. Right now, we're zooming in on a tiny location on a very large map. We'll cross those other bridges and burn them to the ground later. This is a simple series DC circuit, and it may do us some justice to again orient ourselves with some previously discussed properties of simple series DC circuits, namely current, voltage, Ohm's law, power properties, and Kirchoff's voltage law. For us to incorporate the VDR into our toolbox, all our previous properties and analysis techniques must still hold true, and ideally, the VDR should arrive at the exact same value, albeit in a more efficient and timely manner. Let's see if this is the case. The key properties of simple series DC circuits are as follows. Current through elements in a series relationship is the same, because a series connection implies that there is only one path. Given there is only one path, the source current, IS, flows through each element. For this generic series circuit, IS, or source current, equals I1, equals I2, equals I3. Kirchoff's voltage law, the sum of voltage rises equals the sum of voltage drops. If we start here and travel in this direction, we rise E, fall V1, fall V2, fall V3. For this generic series circuit, the Kirchoff's voltage law equation is E equals V1 plus V2 plus V3. We can use Ohm's law to demonstrate that the voltage drop across each element is the current through it times its resistance. V1 equals I1 times R1, V2 equals I2 times R2, V3 equals I3 times R3. Given current in a series circuit is the same, it can be said that the voltage drop across each element will be directly proportional to the resistance. The largest resistor will experience the largest voltage drop, and the smallest resistor will experience the smallest voltage drop. Let's say R1 is the papa bear, R2 is the mama bear, and R3 is the baby bear. We can expect V1 to be larger, then V2, and V2 to be larger than V3. If we insert these observations into our KVL equation, we realize that the voltage drop will be completely dropped across elements in the series path directly in proportion to the element's resistance value. V1 will be larger than V2, which will be larger than V3. Regardless of how voltage is divvied up between these hungry bears, V1 plus V2 plus V3 will still only equal E, never more, never less. We'll make use of this important observation in a moment. If we wanted to simplify the circuit one step further, we could make use of an imaginary resistor RT, where RT equals R1 plus R2 plus R3. The voltage drop across our imaginary resistor RT is obviously equal to the applied voltage E. Ohm's law provides additional proof of this. Because current in a series path is the same, it is a like term in our Kirchoff's voltage law equation, and we can factor it out, where E equals our source current times R1 plus R2 plus R3. Since RT equals R1 plus R2 plus R3, We can also substitute this into our equation. E equals our source current times our total resistance. Finally, we can use any permutation of the power equations from the perspective of the source or the passive elements. Power in always equals power out, where power out equals the summation of individual power dissipations for each element. P in equals P1 plus P2 plus P3. Let's put some numbers into this circuit and solve it the old-fashioned way, namely slugging it out using repetitive permutations of Ohm's law and hammering it repeatedly until the problem just dies of exhaustion and boredom. This should be absolute child's play to you by now. If it isn't, there's a pressing issue that needs to be resolved immediately. Bear with me, this effort is not wasted because I'm going to use this illustration to make an important point. Our supply voltage is 63 volts. R1, our Papa Bear resistor, is 1.8 kiloohms. R2, the Mama Bear resistor, is 900 ohms. R3, the Baby Bear, is 450 ohms. I'm asking for you to solve for the voltage drop across all elements, V1, V2, and V3. By all means, pause the lecture and knock this problem out as a quick warm-up exercise before we learn the VDR. I hate for you to pull a muscle in the middle of this lecture. The total resistance seen by this source is RT equals R1 plus R2 plus R3. 1.8 kiloohms plus 900 ohms plus 450 ohms yields 3,150 ohms of total resistance. The source current is the source voltage divided by the total resistance. 63 volts divided by 3,150 ohms yields 20 milliamperes. The voltage drop across element 1 is the current through it times its resistance. 20 milliamperes times 1.8 kiloohms yields 36 volts. The voltage drop across element 2 is the current through it times its resistance. 20 milliamperes times 900 ohms yields 18 volts. We could use Ohm's law to solve for the voltage drop across R3. However, let's make use of Kirchoff's voltage law instead. Recall our KVL equation for this circuit is E equals V1 plus V2 plus V3. Since we were given E, and just solve for V1 and V2 using Ohm's law, we can substitute these values into our KVL equation and solve for V3. 63 equals 36 plus 18 plus V3. Subtracting 54 from both sides, we find V3 to be 9 volts. Notice our largest resistor, R1, had the largest voltage drop. Our smallest resistor, R3, had the smallest voltage drop. And finally, the summation of all voltage drops equals the voltage rise. I am reasonably confident we're correct. This analysis yielded us correct results, and the techniques I employed should not have been surprising nor new to you. Before we continue on, notice the number of steps it took to solve for 3 unknown quantities. Step 1, we needed to solve for total resistance. Step 2, we needed to solve for source current. Step 3, we used Ohm's law to solve for the voltage drop across resistor 1. Step 4, similarly, we used Ohm's law to solve for the voltage drop across resistor 2. And step 5, we used either Kirchoff's voltage law or Ohm's law to solve for the voltage drop across R3. 5 steps for 3 results. Our answers are correct, and you may be hesitant to consider alternative methods, but trust me, the technique I'm about to introduce to you will yield 3 correct results in 3 easy steps. Our goal is to get the same correct results, only faster. Let's see if this is the case. This is the voltage divider rule. This is not a math class, and this is not a magic show, so I am not going to derive it. It's a waste of time for you to worry about math and magic sleight of hand right now. We're just going to take a brief look at the formula and then apply it to solve for unknown voltage quantities. Ideally, we'll get the same results as our 5-step Ohm's law calculations, only quicker. The voltage divider rule states that the voltage across the element of interest, Vx, is equal to the resistance of the element of interest, Rx, divided by the series resistance of that path, our path, times the total applied voltage of that series path, E path. Notice the emphasis I'm playing on the qualifier of that series path. I'm introducing a truly universal VDR formula right up front with the intention of not baiting and switching you later on. You'll see how this universal VDR formula will be employed in more advanced situations later. If you look at the formula, you'll realize it's a ratio. And the mathematically astute among you will realize that it's accomplishing several calculations at once. I won't go into the details about their calculations, but I will comment on the ratio. Look at the formula. The numerator, the top of the ratio, is the resistor of interest. The denominator, the bottom of the ratio, is the summation of all resistors in that series path. It's like we're dividing up the applied voltage for that series path into a number of pieces, and then allocating the element of interest its representative portion of this whole piece. It makes sense. The VDR is a fractional apportionment of voltage drop based on a resistor size. The largest resistor should get the largest voltage drop. The smallest resistor should get the smallest voltage drop. Let's apply the VDR to this same circuit and see if we can solve for the unknown voltage drops quickly and directly without having to solve for current and resistance intermediaries. To solve for V1, the voltage drop across R1, R1 is our element of interest. R1 goes in the numerator position. The denominator is the resistance of this path. The resistance of this path is R1 plus R2 plus R3. Finally, the applied voltage for this series path is our generic source voltage E. The VDR set up to solve for this problem is as follows. V1 equals R1 divided by the summation of R1 plus R2 plus R3 times E. Substituting in the correct numbers, 1.8K divided by 1.8K plus 900 plus 450 times 63. 1.8K divided by 3150 times 63 yields 36 volts. If you're following along with your Texas Instruments TI-89 Titanium Edition Graphing Scientific Calculator or equivalent, by all means pause the lecture and punch this into your calculator to see if you get the same results. You'll be glad you did. Make the mistakes now, not on a quiz, a lab, or during an exam. Learn from your mistakes and be sufficiently aware enough to never repeat them. The challenge I've observed with students employing the VDR for the first time is not necessarily the concept, but rather the simple mechanics of entering the VDR equation into the calculator properly. Very often they neglect the order of operations. Notice R1 plus R2 plus R3 are all in the denominator. They must be placed within parentheses to make this abundantly clear to the little guy that lives inside your calculator. Without the parentheses, the little guy that lives in the calculator assumes you mean R1 divided by R1 plus R2 plus R3 times E. This will not work. That is not just a wrong answer. In the words of my freshman calculus instructor, that is an absolutely wrong answer, Mr. Pytel. Keep in mind, he said this on the first day of class in front of 192 students. How he knew my name on that first day amid the collected rabble, I will never know. But one thing I can assure you, I never screwed up again, because 191 people laughing at you is an especially strong motivating event. Additionally, sometimes students do the ratio just fine, but then just forget to multiply the ratio by the applied voltage for that series path. 1,800 divided by 3150, or 0.5714, is not the answer. 1,800 divided by 3150 times 63 is. Let's apply the voltage divider rule to find the voltage drop across R2. This time you're on your own. Pause the lecture and set up the VDR to solve for V2. Once you've got the VDR set up, punch it into your calculator and get a result. Once you've got a result and you're confident it's correct, demonstrate your confidence by running down to your local tattoo shop and get it tattooed on your stomach. Take your shirt off and look at yourself in the mirror and press play. The voltage divider rule states the voltage drop across the element of interest is the resistance of the element of interest divided by the resistance of that series path times the applied voltage for that series path. V2, the voltage drop across R2, is equal to R2, our element of interest, divided by the summation of R1 plus R2 plus R3 times E. Substituting in the correct values, 900 divided by 1.8K plus 900 plus 450 times 63, we find V2 to again be 18 volts. The voltage drop across V2 is exactly half that of V1 because it's carrying the same current and the resistance value is half as much. It makes sense. Finally, since we were given our source voltage E, and just solved for V1 and V2 using the VDR, we could use KVL to solve for V3. However, since the VDR is a new toy, I want to play with it till it breaks. Let's use the VDR to solve for V3. V3 equals R3 divided by R1 plus R2 plus R3 times E. I'd normally say substitute in the correct numbers and get a result, but think about it. We're doing the same calculation over and over with only a slight variation every single time. Think about the VDR formula. The voltage divider rule states that the voltage across the element of interest is equal to the resistance of the element of interest divided by the resistance of that series path times the total applied voltage of that series path. The only thing that ever changes about this formula when solving for voltage drop across an element of interest is the element of interest. This is another reason why I like the VDR. It goes well paired with the Texas Instruments TI-89 Titanium Edition Graphing Scientific Calculator or equivalent. These type of calculators typically have a previous results key. Sometimes you can scroll back up to previous calculations and just wipe out a portion of the calculation you just did and insert the new element of interest. If I walk back up to my calculations I just did for V2, scratch out my element of interest, and call it R3, I can press enter and get a result for V3 without even having to enter the equation in my calculator. I mean, how much lazier can you get? What you do with all this newfound free time is your choice. The point is, you'll have a lot more of it if you start working smarter and not harder and routinely employ shortcuts like the VDR. Regardless, the voltage drop across element 3 is 9 volts as expected. Notice we quickly and directly solve for 3 unknown voltages with just 3 calculations, without directly having to solve for total resistance or current. If we still wanted to solve for current, manipulation of Ohm's law using any of the 3 elements would yield the same result. The current through resistor 1 is the voltage across it divided by its resistance. 36 volts divided by 1.8 kiloohms yields 20 milliamperes. Since this is a series relationship, I can be assured that 20 milliamperes travels through the 900 ohm resistor and the 450 ohm resistor. And I can check my work to make sure that's true, where I2 equals V2 divided by R2, 18 volts divided by 900 ohms yields 20 milliamperes. I3 equals V3 divided by R3, 9 volts divided by 450 ohms yields 20 milliamperes. Again, confirming that we can use different methods at different starting points in different sequences to yield the same results, and they should all be correct. Did you enjoy using the VDR? I don't care if you enjoyed it or not. You save time using it. With the time saved, you can do more of the things you do enjoy. Here's another series circuit with the following values. Supply voltage of 54 volts. R1 is a 2.4 kilo ohm resistor in series with R2, a 3.6 kilo ohm resistor. Pause the lecture and apply the VDR to solve for the voltage drop across each element, V1 and V2. Once you've got this information, solve for the current through each element. The voltage divider rule states that the voltage across the element of interest is equal to the resistance of the element of interest divided by the resistance of that series path times the total applied voltage of that series path. To solve for V1, R1 is the element of interest. The resistance of the series path is R1 plus R2, and the total applied voltage is the generic supply voltage E. Substituting in the correct values, we find V1 to be 21.6 volts. Since this is a 2-element series circuit, we could easily solve for V2 using KVL, but since we want some practice using the VDR, let's apply the VDR. Substituting in the correct values, we find V2 equals 29.4 volts. We could solve for current through one of our series elements. I2 equals V2 divided by R2, 29.4 volts divided by 3.6 kilo ohms yields a current draw of roughly 8.2 milliamperes. Since R1 is in series with R2, it can be said, no calculations needed, that current through it is also 8.2 milliamperes. All necessary unknowns have been solved for in 3 quick and direct steps that did not dilly-dally, defer, or delay our immediate satisfaction for results. Get to know the VDR. It will save you time and frustration. As alluded to previously, the VDR is not just limited applications within perfect series circuits. If you've been following this playlist in its intended sequence, understand we've dealt with limited material so far, so I'm purposely restricting the domain of application to just series circuits. We'll expand the use of the VDR in later lectures. However, consider, if you will, the following scenario. Our supply voltage is known at 24 volts. R1 is an unknown resistor with an 8 volt drop across it. R2 is a 390 ohm resistor, and R3 is a 130 ohm resistor. I'm asking you to solve for the unknown voltage drops, V2 and V3, and the unknown resistor R1 using your knowledge of Ohm's law, Kirchoff's voltage law, and the VDR, not necessarily in that order. Pause the lecture and take your best shot at this. Using Kirchoff's voltage law, we can solve for the remaining voltage drop experienced by the two unknown resistors, R2 and R3. Starting here and traveling in this direction, we see a voltage rise of E, a drop of V1, a drop of V2, and a drop of V3. Our KVL equation for this loop is E equals V1 plus V2 plus V3. Substituting in our known E and V1 values and subtracting 8 volts from either side, we find V2 plus V3 equals 16 volts. In order to apply VDR to this in effect partial series circuit, we can use one of two equally valid conceptual arrangements. One, we can just use an imaginary model where a 16 volt source supplies a 390 ohm resistor in series with 130 ohm resistor and take it from there. Or two, we could apply Kirchoff's voltage law to another loop inside our complete series circuit. Starting here and traveling in this direction, we rise 16 volts, fall V2, and fall V3. Using either conceptual arrangement, it can be said that our path of interest is not the series combination of all three elements, but rather just the two remaining elements, R2 and R3. Additionally, it can be said that the applied voltage rise for this path is no longer the full supply voltage of 24 volts, but rather only 16 volts. Either conceptualization yields the undeniable reality that R2 and R3 must proportionally drop 16 volts. The largest resistor of this combination would drop more, and the smallest resistor would drop less. Either way, the summation of those voltage drops will never exceed nor be less than 16 volts. Using the VDR to solve for V2, it can be said that V2 equals R2 divided by the resistance for this smaller path, which is only R2 plus R3, and the applied voltage for this smaller path of 16 volts. Substituting in the appropriate values yields V2 equals 12 volts, with 12 volts being dropped across two resistor combination, of which there is a total voltage rise of 16 volts. A reconfiguration of KVL could be used to solve for V3. Subtracting 12 from both sides yields V3 equals 4 volts. We can also use the VDR to confirm this, where V3 equals R3 divided by R2 plus R3 times 16. Substituting the correct values where R3 is our element of interest, we again find V3 equals 4 volts. Now, knowing the voltage drop across two resistors, one could easily solve for the current through this entire series network. If R2 is a 390 ohm resistor experiencing a 12 volt drop, I2 equals V2 divided by R2. 12 volts divided by 390 ohms yields roughly 30.8 milliamperes of current. Since these three resistors are in series with one another, it can be stated current through R1 and current through R3 is roughly 30.8 milliamperes. Given the unknown resistor R1 is experiencing an 8 volt drop with roughly 30.8 milliamperes of current traveling through it, we can use Ohm's law to solve for the unknown resistance R1, where R1 equals V1 divided by I1. 8 volts divided by roughly 30.8 milliamperes of current yields R1 equals 260 ohms. All unknown quantities have been quickly and directly solved for using KVL, Ohm's law, and the VDR applied to a smaller portion of a larger series circuit. The trick is proper application of the universal VDR, where the denominator includes the resistance of just that path, and the applied voltage is the applied voltage for just that path. Pause to consider an alternate series configuration of the same circuit, where our unknown resistor, R1, is between two known resistors, R2 and R3. The circuit is still supplied by a 24-volt source, and there is still an 8-volt drop across the new location of R1. Is this circuit any different than our previous circuit, and will applications of KVL, Ohm's law, and the VDR yield any different results? The answer is no. The sequential arrangement of resistors within a series network will not affect total resistance. If total resistance is unchanged, source current is unchanged. If source current is unchanged, the voltage drop across individual elements will be unchanged. The only difference between this circuit and our first configuration is the nodes to which individual voltage drops are assigned. Performing a KVL analysis on our circuit, starting here and traveling in this direction, we find a rise of E, a fall of V2, a fall of V1, and a fall of V3. E equals V2 plus V1 plus V3. Substituting in our given values and subtracting 8 from both sides again yields V2 plus V3 equals 16 volts, and we can proceed with our analysis and apply the VDR and Ohm's law as previously to get the same answers. If you want a visualization to accompany this, you can again think of just R2 and R3 in series with one another, supplied by a 16-volt source. Or you can get tricky and think of your smaller path as just not including R1 anymore, and you're passing it by, not paying any attention to it, hoping it won't notice you, kind of like running into your weird lab partner at a cool party. Either way, V2 should equal 12 volts, V3 should equal 4 volts, and R1 should equal 260 ohms. One more example problem before we move on to applications and close up the lecture. This time a 4-part example problem featuring a potentiometer. Part 1 and Part 2 of this illustrated example problem uses a 12-volt source with a 200 ohm resistor in series with a 1 kilo ohm potentiometer hooked up in the following fashion, C to A. In this case, the potentiometer represents an invariable, constant 1 kilo ohm load to the whole series circuit. What is variable, however, is the voltage at the B terminal of the potentiometer with respect to ground. I'll assign nodes in the following fashion. That way no one gets confused between the potentiometer terminals and the nodes. For Part 1, the resistance between B and C is 700 ohms, and the resistance between B and A is the remainder of the 1 kilo ohm potentiometer, or 300 ohms. For Part 2, the resistance between B and C is 400 ohms, and the resistance between B and A is 600 ohms. For both Parts 1 and Part 2, I'm asking you to solve for the voltage drop across the 200 ohm resistor, using nodal notation that's VDC. The voltage drop across the whole potentiometer with respect to ground, in this case, that's VCA. The voltage drop across the top half of the potentiometer, VCB, and finally the voltage drop across the bottom half of the potentiometer, VBA, which, since node A is at ground, is also the voltage at the B terminal with reference to ground. Pause the lecture and take your best shot at applying the VDR to these scenarios. Before doing so, I want you to pause and consider the differences and similarities between these two scenarios. Are there voltage drops and resistances that change? Are there voltage drops and resistances that stay the same? You might save yourself some time if you find scenarios that directly carry over from Part 1 to Part 2 and vice versa. In this scenario, we really have an unchanging 2-element series circuit, in which one of the elements allows for a voltage drop internal to it. Regardless of the position of the B terminal, the source is always seeing a 200 ohm resistor in series with the 1 kilo ohm resistor. Therefore, regardless of the position of the B terminal, the source will still produce the same current. With the same current traveling through these same two resistors, the voltage drop across them will be the same. You should be getting identical results for VDC and VCA for both Part 1 and Part 2. Additionally, since VCA is the voltage drop across the whole potentiometer, and RBC and RAB are those two resistors that make up the potentiometer, it can be stated that the voltage drop across the whole potentiometer is equal to the summation of the two voltage drops internal to the potentiometer, regardless of the position of the B terminal. Again, this should hold true for part 1 and for part 2. VCA should equal VCB plus VBA. Let's set up our voltage divider rule to solve for VDC. VDC equals 200 divided by 1K plus 200 times 12. VDC is 2 volts for part 1 and 2 volts for part 2. VCA is 1K divided by 1K plus 200 times 12, 10 volts for parts 1 and 2. Now we have to dive into the internal workings of the potentiometer for different B terminal positions. Given that there is a 10 volt drop across the entire potentiometer, VCB is that portion of the 10 volts dropped across RCB. VCB therefore is RCB divided by RCB plus RBA times 10 volts. Substituting in the appropriate values, we find VCB to be 7 volts. Solving for VBA, part 1 should experience a 3 volt drop. We're using our VDR for VCB for part 2, and substituting in the correct values, we find VCB to be 4 volts and VBA to be 6 volts. For parts 3 and 4 of our last illustrated example problem, consider the exact same source and the exact same 200 ohm resistor and the exact same 1 kilo ohm potentiometer hooked up in this fashion, where the B2A portion of the potentiometer now represents a 2-terminal variable resistor. For part 3, the resistance between the B and A terminals is 100 ohms, and for part 4, the resistance between the B and A terminals is 400 ohms. I'm going to assign the following nodes and ask kind of the same questions. What is the voltage drop across the 200 ohm resistor, VDB? What is the voltage drop across the whole potentiometer, VCA? What is the voltage drop across the top half of the potentiometer, VCB? And the voltage drop across the bottom half of the potentiometer, VBA, for both parts 3 and part 4. Pause the lecture and take your best shot at applying VDR to these scenarios. Before doing so, I want you to pause and consider differences and similarities between these two scenarios. Are there voltage drops and resistances that change, or do they stay the same? Are there paths that carry current and exhibit a voltage drop? Are there paths that do not carry current and will not exhibit a voltage drop? You can redraw the circuit in any fashion you see fit to visualize this. For both parts 3 and 4, this in effect 2-element series path, current will only flow in this loop, and no current will flow from the B to the unused C terminal of the potentiometer. If no current flows through this portion of the potentiometer, there will be no voltage drop across it. If red represents the potential at node D and blue represents node A at ground, we'll use this nauseating shade of purple to represent the potential at nodes B and C. If B and C are at the same potential, for both parts 3 and 4, we should find VCB to be 0 volts. And given there is no voltage drop from C to B, it can be said that node C will have the same potential as B, and both VCA and VBA should equal each other. One can visualize the RBC portion of the potentiometer as an extraneous resistor just sticking off the side of our 2-resistor series network with no current path. This being said, R1 is a fixed resistor of 200 ohms, and RBA is a variable resistor. Given we can vary RBA up or down, R1 should drop more or less of the applied voltage, and RBA less or more of the applied voltage. As VDB goes up, VBA should go down, and vice versa. But at all times, VDB plus VBA should equal our total applied voltage. Let's see if this is the case. For part 3, where RBA is 100 ohms, VDB equals 200 divided by 200 plus 100 times 12 yields a value of 8 volts. VBA equals 100 divided by 200 plus 100 times 12 volts for a value of 4 volts. For part 4, RBA is 400 ohms. twice as much as the fixed 200 ohm resistor, so RBA should drop twice as much. Let's see if that's the case. 200 divided by 200 plus 400, VDB equals 4 volts. VBA equals 400 divided by 200 plus 400 times 12 volts. VBA equals 8 volts. The hardest part of this 4-part problem probably wasn't the application of the VDR to a 2-element network, one of which was fixed and the other variable. The hardest part was probably the realization that the unused RBC portion of the potentiometer carries no current, and no voltage drop will be exhibited across it. If a path did exist, there would be current flow and attendant voltage drop, but that's clearly not the case. With no flowing current, all of RBC assumes the potential at node B everywhere within it, including the unattached node C. Let's briefly discuss applications not so much of the VDR, but rather voltage dividers. A voltage divider is a series string of identical resistors supplied by a source. A voltage divider's purpose is to take that source and chop it up into voltage values usable as electrical inputs for other circuits. Voltage dividers form the basis of a number of popular and useful electronics, specifically the internal workings of something called the 555 timer, and a common method of converting naturally occurring analog signals to a format compatible with computer processing, a digital signal, via a method called flash or simultaneous analog to digital conversion. Let's take a very brief look at each one. A 555 timer is a popular integrated circuit package used to perform a number of functions, including outputting an electrical pulse for a predetermined amount of time, or creating a digital clock signal with a given frequency and duty cycle. You do not need to understand the internal workings of a 555 timer now, nor even understand digital clocks. But the reason it's called a 555 timer is because of the series string of identical 5 kilo ohm resistors that forms its basis of signal comparison. 555. Get it? It's supplied by a voltage source called VCC. Let's assume VCC is 5 volts with reference to ground. In this case, the 5 volt supply is being split into 3 equal portions, roughly 1 2/3 volts each, dropped across each 5 kilo ohm resistor. With access to the nodes between the resistors, we can gain additional values with reference to ground. If at the VCC node we are at 5 volts higher than ground, and there is a 1 2/3 voltage drop across the first resistor to get to node A, we are now 3 1/3 volts higher than ground. With another 1 2/3 voltage drop across our second identical series resistor, node B is 1 2/3 volt higher than ground. At this point in your career, you needn't worry what the 555 timer is doing with these voltage signals, but for the curious among you, realize the 555 can compare external or internally generated signals with these values. The take-home point about voltage dividers is, with a series string of identical resistors, regardless of the resistor magnitude, they simply equally divide up the applied voltage into equal and identical voltage drops. Let's see if this is the case for this series string of 8 identical resistors supplied by 8 volts. Applying the VDR to solve for the voltage drop Vx across one of the resistors, we find the following. In this case, Rx is the element of interest, one of the identical resistors. The total resistance of 8 identical resistors in series would be 8 times Rx, times the total applied voltage for this path. In this case, the identical resistance value cancels out, and the voltage drop across one of the individual resistors would be 1/8 of our applied reference voltage. It makes sense. Given we're supplying our voltage divider with 8 volts in the first place, we conveniently find that the voltage drop across each resistor to be 1 volt. Given we have a rise of 8 volts, and we drop 1 volt every time we progress to the next node, the nodal voltages with reference to ground would be as follows. This doesn't seem especially earth-shattering until this voltage divider is applied to perform some function. In this case, the voltage divider is again forming a basis of comparison to another signal. For this application, the same input signal in blue is being compared to all nodal voltages provided by the voltage divider. This is flash, sometimes called simultaneous analog to digital conversion. As I previously mentioned, a common method of converting naturally occurring analog signals to a format compatible with computer processing, a digital signal, basically a combination of ones and zeros, i.e. the presence or absence of voltage. Each one of these little triangle things is a voltage comparator, which outputs a digital 1 or true if its plus input on the top is greater than its minus input on the bottom, and a digital 0 or false if its plus input is lower than its negative input. It makes sense. Pluses ordinarily should be higher than minuses. Here's the neat part. This whole network of voltage comparators is comparing the same input signal in blue to an array of different voltages provided by the voltage divider. If the input signal is 4.3 volts, the comparator comparing 4.3 volts with 4 volts is true, as are all the ones below it. The comparator above it is comparing 4.3 volts to 5 volts, and it issues a false, as do all the higher order comparators. The output of these comparators is now fed to an encoder, or more specifically, a priority encoder, in that the higher weighted input receives priority. The highest input to this priority encoder is 4, and the internal circuitry within the priority encoder outputs the digital code for 4, 1, 0, 0, in this case the 3-bit representation of 4. Do you see what this voltage divider, the comparator network, and the priority encoder is doing? It took an endlessly variant analog signal and packaged it into a format usable by a computer, notably a string of ones and zeros, the presence or absence of a voltage. A computer can now use this digitized data to make a decision. Let's say that incoming analog voltage is the output of some transducer. A transducer, if you'll recall, is a sensing device that outputs a proportional voltage or current signal in response to a physical, temperature, chemical, or some other change. The flash analog to digital converter is in effect converting this 4.3 volt analog signal to the digital number 4, something it now could compare another digital value with. If the analog input was to rise to 6.4 volts, the 7 volt comparator would issue a false or digital 0, and the 6 volt comparator would issue a true or digital 1, as would all lower order comparators. The highest input being asserted on the priority encoder is 6, and the encoding function would output the 3-bit binary code for 6, 1, 1, 0. It may seem we've lost some granularity or resolution with this type of a circuit, and at this level of simplification we have. However, understand the conversion of naturally occurring analog signals to a digital format comes with several inherent advantages. Notably that digital data is easier to store and process and less affected by electrical noise. The take-home point to this application is that the voltage divider forms the backbone of this analog to digital converter by providing an array of reference signals against which incoming analog data can be compared. If we wanted to increase the resolution or granularity of our system, we could use a voltage divider with 16 identical resistors and be accurate to the half volt, or 32 identical resistors to be accurate to the quarter volt, and so on into imperceptible levels of distinguishability. Okay, I think we've done enough reps of the VDR that you should feel comfortable with applying it to series DC circuits. I'll show you how to apply the VDR to other, more advanced scenarios as occasions present themselves in later lectures. In conclusion, this lecture presented the voltage divider rule and applied it to several simple series DC circuits. We found it quickly and directly solved for unknown voltage quantities without having to solve for intermediate values. The time you save is valuable and is one of my favorite techniques. With a little practice, I have no doubt this will become one of your favorite techniques too. Again, it's quick, it's direct, and it's effective. Remember to review the voltage divider rule as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.